Hi, thanks for joining me in another video on thermometry. And in this video, we're going to talk about the performance characteristics of thermometers. As we discussed before, performance characteristics can be broken down into either the static or dynamic performance characteristics. When discussing the static performance characteristics of thermometers, we're looking at the property known as sensitivity and also the process of calibration. Sensitivity we'll talk about later on as we go through each instrument, each thermometer type. Calibration we'll do in lab. What we're going to do now is discuss dynamic performance characteristics, and with that we are going to spend a little time talking about time constants. We'll start our discussion of the dynamic performance characteristics of a thermometer by looking at its thermal balance. We'll look at the thermal energy that was gained or lost by a thermometer, represented by the mass, the specific heat of the thermometer, and the change in temperature. And that's balanced by the thermal energy that's lost or gained by the air. And that happens over a period of time, dt. The thermal energy lost or gained by the air depends upon the surface area of the thermometer, how much area is able to conduct or transfer energy away from it, and also the heat transfer coefficient, which is a function of the wind speed and also the air density. The thermal energy lost or gained by the air also depends upon the temperature of the air and the temperature of the thermometer. We can rearrange this equation by bringing the time over to the left side, that would be in the denominator, and then through the associative principle, multiply U and A times the temperatures, the two temperatures on the right side. And then we'll solve for the input temperature. Looking at this equation, gee, it looks a lot like a first-order differential equation. With dt over T, we have the derivative of temperature and then temperature. I know this is getting a little bit complex, and only algebra is required for this class. But we could rearrange this algebraically by bringing U and A over to the left side, and that leaves just Ti on the other side. Ti is the input temperature, meaning that's the temperature of the air. And then the T's that we see on the left side are the temperature of the thermometer. An equation like this has a solution. If we combine the terms on the left side of the equation, mc divided by ua, and call that tau, then that makes this equation look a lot simpler. And that's what we see in the bottom. We have tau with dt over t, our derivative, plus T, which is the sensor temperature, is equal to the input temperature, meaning the temperature of the air. As I said, this looks like a differential equation, and there is a known solution for this. So what we're going to do is look at temperature changes in our atmosphere and watch how the thermometer responds. Since we've already been dealing with differential equations, well, we're going to use a solution to the differential equation. But I don't want this to get any more complex. So we won't look at ramp inputs, and we won't look at sinusoidal inputs of temperature. In other words, like the diurnal temperature change from day to night, that would be sinusoidal. And ramp input would be just a simple change in temperature with time. Instead, we're going to take a more simpler approach. And we're going to look at only the step input. What we now have is a solution for this differential equation. We started out, as the graph shows, at some temperature T0, and then changed the temperature instantaneously to a new temperature TA. In this graph, it shows this is done instantaneously and the temperature is dropping at TA. It could also increase from T0 to TA, but here we're showing it dropping. An example of this is if you had a thermometer at room temperature and then suddenly plunged it into a cold bath of ice water at a temperature of 0 degrees Celsius. That happens instantaneously. The temperature changes. And we'd like to see how the thermometer responds. And that's what this equation shows. It shows that our initial temperature is T0, our final temperature is TA, and we'll see what the temperature of the thermometer is, T, at some time, small t, in the future. And that is a function of the time constant tau. So this is getting a little bit complicated. What these graphs show, and what we're doing, is changing the temperature instantaneously from T0 to TA. That's our input. On the right side, the graph shows how our thermometer responds. It doesn't instantaneously change temperature. It changes more slowly. It changes exponentially. And eventually, it does reach the final temperature, TA, but after a period of time. We're going to define time constant as the time required for an instrument to indicate 63.2% of a total change. That might seem like an arbitrary number, 63.2%, but actually that comes from our equation that we just solved. We'll see shortly in the next slide that 63.2% is actually 1 minus 1 over E, or 36.8%. So in other words, time constant is the time it takes for the temperature to change to 63.2% or within 36.8% of the final value. Here's the equation I was telling you about, and actually we had solved this earlier. What it shows is the temperature at any particular time. Well, if we put the time constant in for the time, in other words, if we have tau over tau in the exponent, that gives us e raised to the minus 1. And e raised to the minus 1 is actually 0.368, which is 63.2% of a change. So that is what the temperature will be at the time constant. You can also figure out the time constant graphically. And to do that, you would need to plot the temperature with time of the thermometer. And that's the solid red line going down. You see that that's kind of an exponential curve. The actual temperature, this is where you take the thermometer from room temperature and plunge it into the ice bath, is the dashed line that's going straight down. That's the instantaneous change in temperature. And you'll see that when you get within 36.8% of the final value, that is your time constant. That means the temperature of the thermometer changed 63.2% when it reaches the time constant. So if you get the time at which that occurs, well, that's your time constant, the time that it takes for the thermometer to reach 63.2%, respond 63.2% of the change. Another way to determine the time constant is to take the equation we had earlier and solve for tau. Tau is our time constant. In doing that, just takes a little bit of algebra, but we end up with the equation that you see on the bottom. To figure out the time constant, you would need to know the initial temperature, the starting temperature. You would need to know the final temperature, which is TA, and also you would need to know the time t at which temperature T occurs. So putting those values in, you would get the time constant. Time constants for different types of thermometers vary. Electronic sensors, such as an RTD or a thermistor, have a very quick response, and their time constants are on the order of only tenths of seconds. Whereas a liquid in glass, like a mercury in glass thermometer, they're a little bit slower. They've got more mass, so their time constant may be on the order of a minute or so. So there are a number of ways which we can calculate the time constant. We went over two of those already. We can do it graphically. We can do it knowing the initial and final temperature, and then the temperature at time t. And the third way is by knowing the characteristics of the thermometer. The characteristics would be the mass of the thermometer, its specific heat, the heat transfer coefficient, and then finally, the effective area of heat transfer for the thermometer. The equation shows us that the time constant depends upon the heat capacity of the sensor, the shape of the sensor, how big is it, how much surface area there is, the heat transfer capabilities of the medium surrounding the sensor, and then finally the wind speed or the fluid, which is a function of U. So that is the dynamic response of a thermometer.